MSU physicist Nico Yunes. Welcome back, friend.
Thank you.
That's right. I forgot your fanfare. Looking back on our recent conversations, we started this series with gravity. We've moved to time. We've discussed space. Last week, it was a sort of a sidestep for the big Super Bowl game, North American football, when we discussed the physics of North American football. But today, I know our topic is going to be space-time. But before we get there, there is a major scientific group that has an announcement coming tomorrow morning, I believe, as you just told me, at 8:30.
Yeah, I think that's right. 8:30 our time. The LIGO scientific collaboration. So LIGO is a massive instrument in the United States. There's one machine in Washington State. That's not that far away from here, near the nuclear reservoir area, wasteland, whatever it's called.
And what does LIGO do?
It detects, or it's trying to detect, Einstein's last prediction. Yeah, well, more or less. So Einstein predicted the theory of general relativity, or came up with a theory of general relativity in November/March of 1915, 1916. So it's like right now, the centennial. So we're all celebrating, big party, yada, yada. And coincidentally, there has been a major push to detect this last prediction of Einstein's theory, the existence of gravitational waves that have only been seen indirectly before through observations of stars and neutron stars, like we call them pulsars, but never directly. We never had constructed a machine that could detect these waves, and the effect of these waves on matter is so minuscule, it's so small, it's really hard to measure. And LIGO has been, they started thinking about LIGO in the 1970s. And then it went through a lot of phases of design and redesign, and the technology was just not there. Like, we didn't have the mirrors we needed, or the lasers we needed, or the vacuum systems we needed, or the seismic isolation we needed. So all of that technology, scientists and engineers and technicians had to work together to invent. And then once the technology was there, it could all be put together, and it was finally turned on in its advanced configuration about 4 or 5 months ago, something like that. And it was on for 3 months. They did their first observing run, and they will announce their results tomorrow morning. So there's a big drum roll that's going on. It's going to extend from now until tomorrow morning. And so we'll just have to tune in and see what they say.
Because very briefly, my understanding of gravitational waves is it is a wave that causes slight ripples in time-space, which we are going to discuss after this first commercial break. Is that an accurate definition of gravitational waves?
Yeah, so remember the first time you brought me here, you asked me about gravity. And so we talked about that, and then we sort of took 1,500 steps back and went back to what is space and what is time, and that's all fine and dandy. But when we talked about gravity, we were saying it's a force. And moreover, it's a force that can be thought of as the curving of space-time. Well, if you have a massive object that's moving around, it's curving space-time, and on top of that, it's moving around another massive object, the curvature of space-time is going to induce ripples in space-time. They're going to propagate out. There's going to be vibrations in gravity, so oscillations in the force, in the gravity force. So if you want, as a gravity wave is going by, a matter that gets crashed in quotation marks, or it feels this gravitational waves. It doesn't really get crashed. It just gets stretched and compressed slightly. It's just that the change in separation, it's so tiny. It's so ridiculously tiny that you can't possibly see it with the naked eye. You can't even see it with a microscope. We're talking about changes due to a gravitational wave, say, hitting a human of, smaller than 1/1000th the size of the nucleus.
Oh, wow. That's really small.
That's really tiny. That's not something you can see. It's obviously not something that has any effect on health. It's not like you gravitational wave tan outside, and that has any type of health benefit or problem to you. But yeah.
So expect the major announcement from the people tomorrow morning, 8:30, approximately 8:30 our time.
Yep.
And I'll look forward to that. I'm going to take a quick commercial break, and we'll come back and we can pick up our conversation on time-space.
Let's go for it.
Space-time. Is it space-time or time-space?
It's Pacha.
Pacha. Pacha, what is space-time? Or what is Pacha?
So it was really weird, right? So I was, I knew that we were going to talk about space-time because we had talked about space and we had talked about time, so it made sense to talk about the two together. And then so I Wikipedia it because that's what scientists do. No, I'm just kidding. That's not what scientists do. That's what Nico does when he's bored. And I was looking at the historical use of the word space-time. Who came up with space-time first? And the earliest reference I found was from the Inca Empire, in Central America. The people that love to cut hearts out and sacrifice people to the gods.
Exactly. And they played a sport that if you lost, you died.
Yeah, it was like basketball.
Exactly.
Yeah. So the Incas, fascinating people. They thought of space and time as a single concept. They weren't two different things, space and time. They were a single thing. Mm-hmm. They were a unified thing, okay? And they called this thing Pacha. Which, by the way, is where the word Pachamama comes from the Quechua. I did not know this. A professor at the university who studies, who is in the education department, had to explain this to me. I was completely unaware. Pachamama is a word that derives from Pacha, that comes from the Quechua, who apparently were somehow related or descendants from the Incas. And Pachamama means Mother Earth. Mama means mother, Pacha means earth or the whole. So the Inca reference of space and time as a single concept is like thinking of the whole thing, right? It's not just where you are. It's like, it's not just that we are here at the radio station. It's that we are here at the radio station right now. That defines an event. It's the whole. Mm-hmm. And then it was funny. I kept on looking at this. And, Einstein came up with a theory of general relativity in 1915, 1916. But it turns out people have been talking about space-time way before that. Like Edgar Allan Poe talks about it in an essay on cosmology entitled Eureka. H.G. Wells in The Time Machine talks about it in 1895. Marcel Proust in the novel Swann's Way in 1913 also talks about, the space-time continuum, if you think about it. Mm-hmm. And then, of course, mathematicians, Minkowski, Lagrange, they all predated Einstein. They were already trying to unify space and time.
So these ideas that are being examined and proven and or verified in modern physics are not new ideas. It's just we now have the technology to measure and monitor and confirm these ideas?
Well, right. So the ideas are not new, but the precision to which we are formalizing these ideas, that is new. The fact that we can put these ideas into mathematics, which happens to apparently be the language of the universe, that is new. And the fact that we can solve this mathematics to make predictions, that is also new. And of course, the fact that we have technology, or we can at least invent machines that can test and verify these predictions, is also key. The Incas didn't have any of that.
So just for the sake of conversation, when we are talking about space-time or Pacha, how do you define space-time or Pacha?
Yeah, so now that we've talked about space and we talked about time, space-time is actually quite easy. It's the union of space and time. It's a continuum, right? So we talked about space. What space? It was like we were talking about measuring separations, right? So we were talking about, putting rods between two people to measure the distance between two people, like a meter stick. And then you can put another meter stick, and you can put another meter stick. And because there's three spatial dimensions, you can do this as, left, right, in front of you and behind you, and then up and down. Essentially, you're building a building, right, out of rods. And if you think about it, that is three-dimensional space, is the measurement of distances in three-dimensional.
And you may know, because this sounds very similar to, I forget the gentleman who proved the curvature of the Earth by putting a rod in Alexandria and a rod somewhere else in the Middle East, and he measured the length of the shadow it cast at the same time, and that's how they proved the curvature of the Earth.
I bet you there was some Greek person.
I can't I can't remember his name, but I remember that from basic, probably 8th grade science class.
Yeah, that's right. So you can think of space in terms of these rods. And what is space-time? If you now put a clock at the intersection of every single one of these rods, a clock that can measure time. Of course, if time is absolute, one clock is enough to measure time everywhere inside of your building. But because time is not absolute, time is relative, then you actually have to put a clock at every point where the rods intersect. Then this collection of rods that form a building with clocks everywhere, that is space-time.
Okay. And Nico, only because, I'm a big science fiction fan as well. And it's often referred to as, you hear James T. Kirk from Star Trek discussing the folding of space-time.
You've just revealed your age. I would have said Jean-Luc Picard, but okay.
We'll be back. I want to find out, is it possible? Is it theoretically possible to fold space-time? Because if we did, we would be able to travel great distances. We left off after a basic example of what space-time is, and you chided me for my reference of James T. Kirk in the folding of space-time. Is it theoretically possible to fold space-time?
It is.
So we can travel great distances.
No, it can't.
Why not?
Because we can't go through the hole. Yeah, so indeed, there is, back in the 50s or something like that, Einstein and his postdoc, Rosen, came up with a solution to his equations that described a black hole, which is, remember, you think about it, it's like the curvature of space-time. So you can imagine it, even though it's not realistic, as a funnel in space-time. And they said, what if that funnel of space-time connects to another funnel, that just opens up somewhere else in the universe?
See, and that's brought up in Deep Space Nine, where they travel through the wormhole.
Well, right. That's a wormhole. In physics, we call that an Einstein-Rosen bridge.
Okay.
But in science fiction, that's called a wormhole. So another way of visualizing is you take a piece of paper and you fold it in half, and then you take a pencil and then you puncture the two pieces of paper, the two sides, right? And so the idea of a wormhole is that instead of going all the way around the paper, you just go through the hole and appear somehow on the other side, and you've traveled a very large distance in a very short amount of time, sort of, evading the fact that you can't physically travel faster than the speed of light, but because, because space-time can bend, then you can sort of trick nature this way. Little problem, though.
Yes, I'm guessing this is where the gravitational forces rip you apart.
Well, yeah, something has to keep this hole open. And the only thing that can do that is matter, like some sort of fluid with negative mass. And the last time I weighed myself, I had positive mass. I'm pretty sure you also have positive mass.
Yes.
I can't imagine anything that has negative mass. It just doesn't make any sense to us. It has never been observed in nature. It has never been observed in the lab. It has nothing to do with dark energy. It has nothing to do with dark matter, which are other aspects of the universe that we don't fully understand. But negative mass is just weird. And so there's no way to keep this bridge open.
Is this what we know in the science fiction world as antimatter?
No. Antimatter is regular matter with the opposite charge.
Oh, okay. So antimatter is a real thing that actually exists.
Yes.
But
like, for example, positrons are the antiparticles of electrons. And those have been constructed. People have constructed anti-hydrogen.
Okay. But can we have matter with negative mass?
No. Not that we know of, at least.
Right.
There's no theories, there's no experiments, there's no observations that indicate the existence of something with negative mass. Oh, I don't know what that would mean. That would be like having an object that instead of feeling gravity as an attractive force, it feels gravity as a repulsive force. It would be like an anti-gravity type thing. And no, we're not talking about a hovercraft. It's not Back to the Future, Chris. That you can do with electromagnetic forces. You can have electricity and magnetism push you up and support you up in midair, fighting gravity. But there's no fluid, no matter that just reacts to gravity in the opposite way than regular matter. Gravity is attractive as far as we know, and that's why there's no negative matter. It has nothing to do with antimatter.
And finally, because we're just about to run out of time, Nico, as we discuss space-time here, why is the understanding of the physics of space-time important in my daily life? How do physics apply in my daily life when it comes to this matter?
Well, it's super important because this goes back, and I'm going to sound repetitive here, but
Okay.
it matters from the point of view of accurately calculating distances and accurately calculating messages. For example, I was talking about the GPS, right? So the GPS satellites function via triangulation, right? Or trilateration, to be precise. And they carry clocks in those satellites, and we have clocks too in our receivers here. So in order to properly measure distances, we need to know how time dilates or speeds up, if you want, due to these clocks and these measurements happening at different positions in the gravitational field, like we call it. So different positions in the sky at different heights, as well as at different velocities. So when something moves really fast, time slows down. And when something is very close to a strong gravitational field, a strong gravity, then time also slows down. We saw that in Interstellar. So, for example, I actually calculated this for you. You know, who do you think is the fastest runner, sprinter on Earth?
Oh, Bolt.
Bolt.
Yes.
100 meters in 9.58 seconds. Okay?
Yes.
Imagine that he could run at that speed, which is not possible, for an entire marathon.
Yes.
Okay, or something like that. Let's assume that he's running at that velocity for 3 hours. He's moving really fast, so his internal clock slows down, but only by 6 picoseconds. So 6 times 10 to the minus 12 seconds. That's how much his clock slowed down. However, the GPS satellite up in orbit is traveling at 14,000 kilometers per hour. So in a day, its clocks slow down relative to clocks on the surface by 7 microseconds. And if you don't take all of these things into account, which is a complete consequence of the space-time continuum and of general relativity, then you would get the synchronization of the clocks wrong, which then means you would get distances measured with your GPS devices completely wrong in a very short amount of time. So you couldn't land planes,
right.
You couldn't find your favorite Chinese restaurant. It would be a huge problem.
So Usain Bolt is probably constantly asking somebody for the correct time so he can reset his watch.
That's right. He carries a very precise watch.
Well, Nico Yunes, unfortunately, we're out of time this week. I appreciate the explanation and conversation regarding space-time this week and look forward to the next conversation. I will not be here next week.
Boo!
But I hope you will. Tom Eaglehoff will be, filling in for me. I look forward to the conversation 2 weeks with you from now because, as I said, I will not be here next Wednesday. As always, thank you for your time, sir.
Thank you.